Welcome to Lesson 3, Example 2, and it is asking for the maximum moment, and the maximum stress. And what we're going to do is start with the shear and moment diagram and figure out our reactions, and then figure out what our max shear is and our max moment is. And we start by finding reactions using your equations of equilibrium. And just knowing what you know, usually it's going to start off with the sum of the moments about a point, and we define point A. Actually, I need to do this as well. Make an equivalent load. So that'd be 80 times 500 equals 40,000 pounds. Alright, wow, that's quite large. Does that make sense? No, it does not, because it's not times 500. I don't know what I was thinking right there. It's going to be 80 times 14. Is there? That seems a little bit more realistic. Okay, 1,120 pounds. Alright, so let's go back to our sum of the moments about point A. Go from left to right. AY times 0 equals 0. Then we're going to have, it's going to be a positive, because it's going to make a positive moment, pounds, times, that's halfway, so that's going to be 7 foot. And then we're also going to have a positive 500 pounds times 10 foot. 14 minus 4 is 10. And then we're going to have a negative by. Since it's going to make a negative moment times 14 foot. And let's go ahead and solve. 1120 times 7 plus 500 times 10 divided by 14. And we have by equals 917.1 pounds. And then we want to sum the forces in the y direction. Go from left to right. We have AY going up. We have negative 1120 pounds, negative 500 pounds. And we have a positive BY, which is 917.1 pounds. We do the math. 1120 plus 500 minus 917.1, and you get AY equals 702.9 pounds. Alright, so we now have our reactions. Let's go ahead and write them over there. 702.9 pounds and 917.1 pounds. Let's go ahead and switch colors to do our shear diagram. Try to line it up best we can. Life isn't perfect. We go up 702. That should be our max shear. 9. This is going to all be in pounds. I'm not going to label it. It's going to go down at a linear slope until we hit, remember, get rid of your equivalent load and you want to go back to your distributed load until you hit 500. Which, let's just figure out what that is. So you're going to have what? That's 4, so you're going to have 10. 80 times 10 is 800. Does that make sense? Yes. 800. So you have 702.9 minus 800 equals negative 97. So you're going to be a negative 97 about right there. 97.1 to be exact. Then our slope is negative 80 times x. So it'd be 702.9 minus 80x is that equation. And x starts right here. Alright, we're at 97.1, negative 97.1. We want to go down 500, which that's easy. Negative 597.1. And then we want to go down at negative 80 again, slope, 4 foot times 80 pounds per foot. And we have, I messed that up, negative, we should have 320, so that's 320 plus 597.1, and we have negative 917.1. And then 917.1 go up, and you get 0. Alright, there's our shear diagram, and let's go ahead. I've said in the past that your maximum, the point where your shear diagram crosses the 0, the axis here, is where your maximum moment's going to be. So let's go ahead and figure this out. And as like I said earlier, let's say Vx equals 0, because that's what we want to figure out, right? When is the v is a function of x equals 0, at what point x, and so Vx equals 0, and we have 702.9 minus 80, because we have 80, and that's going to be x. Well, we want to figure out when it's hitting 0 right here. It starts at 702.9, it goes down 80 per foot, so what foot is equal 0? So that's pretty easy. 702.9 divided by 80, x equals 8.79. Not exactly, but close enough. So that's x right there. Alright, that should be our point of maximum moment. Now let's go ahead and do the moment diagram. We'll go back to yellow or gold. And this is all going to be a positive moment. So I'll make our moment diagram a little bit lower and give some space ahead, up top. And it's starting off going maximum, right? And then it's slowing down till it gets to 0 slope right here. Because it's hitting 0, that means your slope equals 0. So that should, that's a perpendicular line. Wait, perpendicular, parallel. Anyways, that line's just barely intersecting that, if that makes any sense. It goes to a 0 slope right here, and then it goes to max slope over here. And that maximum is the area under what we'll call A1 right here. And that is, let's write it over here, A1 equals, and you can see our max shear in the beam is right there. And this will equal our maximum moment. So I'll go ahead and write it down. 0.5, because it's a triangle, 702.9 pounds times x feet, which is 8.79, and we get, which is also our max moment, 702.9 half 8.79, 3,089.2, let's say, and that's foot pounds. Alright, and we know that's going to be our maximum moment. You could figure this out. It's going to start at 0, slowly go down, and then it's going to go down faster and go down even more faster. If that's a good English right there. I speak good English. I speak English very good. Anyways, and it'll end at 0. So this is our maximum moment. Let's go ahead and circle that, or box it. Alright, so we found our Mmax. Now we need to find our maximum stress. And if you remember, our stress equation here is stress and bending equals MC over I, or M over S, which is the moment over section modulus. And typically you'll use this when you have defined shapes like 2x4s or or your I-beams. When you open up your steelbook, you'll see a bunch of S's. You also see I's, but S is just a shortcut. Instead of having to figure out an extra C over I, you just have to have one step. Makes it a little bit more easy. Alright, and we want to take a look at the 2x12, because that's what it says we had, is a 2x12 right here. And on 2x12 says that its section modulus is 31.64, and that's on the section properties of standard dressed sawn lumber again, that table. So we said, where are we at? 3089.2 foot-pounds. 12 inches per foot, and divide that by the, what was it again? We said 2x12, 31.64 inches cubed, and we come out with 3089.2 times 12 divided by 31.64 equals 1171.6 PSI. And let's go ahead and check that. They said the maximum fiber stress equals 1170. 1171, close enough. So we're good. We are good for bending. Let's take a quick look at the shear stress. The horizontal shear, at least. And since this is a rectangular section, we can use the simplified equation, which is 3V over 2BD. And that equals, actually I want to take a look at it. That's what we're going to do in the next example. So I won't do this yet. Forget about that. So we did the design for the force of bending. And remember, this MC over I is the extreme fiber, and that's what they're asking for. And when I say extreme fiber, remember that we're taking a look at this. I can't draw a straight line for the life of me. Let's switch colors. Here is your section. So you take a cut, and it's gonna actually, let's not do that. Let's do this. And remember, these are going to be, if it's positive, then we could look at it this way. Oh shoot. The top flange is in tension, and the bottom flange is in top flange is in tension, bottom flange is in, I keep on saying the wrong one. Alright, the bottom flange is in tension because it's going to be stretched. The top flange is in compression. And hopefully you can see that the top right here is the extreme fiber, and this is the force in bending. It's going to be 1171.6 psi at this point. Or if you're looking at it from the side, it's at this point. And if you're asking, hey, what is the force of the stress in bending at the neutral axis? Well, you say, oh, it's 0, and it's always going to be 0 because that's what the neutral axis is defined as. It's the point of 0 for stress. And if you could say, a more accurate would say, did they ask for tension? It would be compression up here and then tension down here. 117.1.6 psi. Alright. Good luck, and I guess I'll see you on the next video.